Hi everyone, Mr. Lee here. In this video, I want to go over a couple of the more advanced centripetal motion type of problems that you could very well encounter. Alright, so let's head on in. Now, in this first type of problem, we are going to do a tetherball kind of situation where we have a giant pole, and attached to that giant pole is a rope, and attached to that rope is a ball, right? And so you might have seen this while growing up, where you would have different people like around here, and then they would take turns hitting the ball around. If they miss, like they lose a point or something like that. So in this scenario here, we have a ball that's attached to a rope, and the rope and the pole has a angle of theta, okay, but it's swinging around. All right, so the steps to solving these problems are exactly the same. So the very first thing that I want to do is I want to draw a free body diagram. So I'm going to do this in red. So my very first force I want to draw is the force of gravity going down. And the next one that I want to draw is the force of tension. And the tension is going to be going at an angle like so. Okay, so my next step and my next suggestion to you is, if you have like a drawing like this, take a step back away from the drawing and just draw the free body diagram itself. So we have a ball, and we have the force of gravity going down, and we have a angled tension force like so. Okay, so if this is a free body diagram, we learned that whenever you have an angled force, the best thing to do is to actually break it down into its components. And so I'm going to do the components in blue, but the only one that is angled is the tension one, and we can break it down into its T sub x and a T sub y, with that being the 90 degrees and this being the theta. All right. Now, if this is the angle theta, we can say that T sub y is going to be T cosine of theta, because this angle is adjacent to this vertical axis. And over here we have the opposite, so which is the T sine of theta. All right. Now, if we take a look back at this drawing here, because we came up with the free body diagram and we even came up with the component version, we have to think to ourselves, at that exact moment, what is the axis of rotation? Are we looking at a vertical, okay, a vertical spin, or are we looking more at a horizontal spin? Okay, so this is my best rendition of a 3D drawing, but the answer is we're looking at a horizontal spin. And what I mean by that is, if this is the pole and this is like the base and this is the ball, this ball will be swinging around in this axis here, in this horizontal axis here. Okay, so we're going to create a net force equation for the horizontal axis. So f of y, that should be f of c is equal to mass times the centripetal acceleration. And if we take a look here, the only force that is along this horizontal axis is T sub x. So Tx is equal to MAC. And we could break this out even more and say that is T sine theta is equal to M Vt squared divided by R. So something like that. Okay, and that will be our net force formula. All right, so this is something that's unique, because if we take a look at this free body diagram, what this equation tells us that only and this is very important, only the horizontal component of the tension is causing the rotational motion. Okay, so only, I'm gonna underline it here, only Tx is actually causing this ball to swing in a circle. So you might be asking yourself, what about Ty? What about Ty and the weight? Well, to answer that, we can create a net force y equation. Okay, because we know that in the y-axis we have Ty minus f of g, and it's not accelerating vertically. And so we can say that it's 0. At that moment, it's not moving up and down, so it'll be 0. And so we can say that the vertical component here, that the only reason that we have the vertical component of tension is to hold up the weight of the object, or the weight of the ball itself. All right, so we have two ways of describing this tetherball type of scenario. Okay. So I want to show you that because you might come across an object that's spinning around in a horizontal axis, but there's going to be a angled component to it. So the next one that I want to do, this next problem requires a little bit of setup because we're going to have to revisit a couple of Newton's laws here. Okay, so let's say that we had a platform, right? A platform, we can think of it as like a book or like a table or like a tablecloth, right? Something that is there, that is flat. And on top of it, let's say we have a glass or a plastic cup of some sorts. Let's say it's a mug. All right, so we have a mug. And inside this mug, we have, I don't know, coffee. All right. Now, in our world, right? So if, let's say this is, I don't know, paper or tablecloth or, whatever you want to call it, if this is a book. In our world, when we pull horizontally on this surface, the mug also moves along with the surface, right? I'm just going to say book, right? This is a textbook. So if I pull on the book to the left, the coffee mug will also move to the left. Now, we got to think about this. Did we exert a force on the mug? The answer is no. I never touched the mug. I only touched the book. Okay. So according to Newton's second law, okay, the only reason why the book accelerated, okay, from rest, so it sped up, is because I exerted a pull, right? I pulled on the book, therefore the book sped up and accelerated. I never touched the coffee mug. So what did cause the coffee mug to also accelerate? So in order to approach this problem, we got to imagine a world where this wouldn't happen, and that would be a world without friction, if there was zero friction. So in a world with zero friction, right, I'm just going to redraw it. So there's going to be no friction. Okay, so there's no friction here. If I were to do the same demo, okay, and I were to pull the book to the left, because in this world there's no friction, what would happen is that this mug would just simply fall down. And we could recreate this in the real world, in a world with friction, by pulling on that book super quick. Because if we pull on the book super quick, the force of friction kinetic would be far less. So if there's like two less than signs, it means that it's super small than the force of the pull, right? And so in this case, the coffee mug, the force of friction can't be dragged along with the book, and so the coffee mug will just fall down, much like in a world without friction. So if you did do that demo that I showed you in the demo video, like that's the reason why when you exert a force on the object and you pull on it super quick, that's why it falls down, because the force of friction isn't big enough. Okay, so here, if we were to take a look at the scenario and we say, okay, so if there was no friction, this book or this mug would just fall down, right? And it will crash onto the floor. So that must mean that here in the real world, the reason why the coffee mug is moving with the book is because of a force of friction, right? So how do I know that the force of friction is pushing it to the left, you might be thinking? Well, not only because the mug is accelerating to the left when I pull on the book, but if we were to imagine a world where there is no friction. Okay, so this is what we call frame of reference. It's a very important tool for us as physicists. Frame of reference states that if we were to just hone in on the coffee mug, right? So our sights are on the coffee mug. We can say that the coffee mug never moves, but the surface below it is moving to the left. Okay, so I'm going to say it one more time. If we're focusing just on the coffee mug, the surface below it is moving to the left. The coffee mug does not move at all. Okay? And so if we were to do the reverse and we were to hone in on the textbook, right? I hone in on the textbook. If I hone in on the textbook, even though that I'm pulling on the textbook because my focus is on the textbook, we can say that the textbook never moves. The world is moving around the textbook. And so if I'm laser focused on the textbook and I'm looking at the textbook only, it looks as if the coffee mug moves to the right. And you have to use your imagination a little bit. Okay, so what this means is that if I'm looking at the textbook and if I'm pulling the textbook to the left, if I were to draw this like animation style, right? I'm focusing on the textbook. So my frame of reference is a textbook. If the coffee mug was here, okay, along this axis, as I'm pulling the textbook, the coffee mug will be moving further away from the middle. Okay, I'm going to do this again. Okay, once again, I focus on the textbook, and the coffee mug is moving further away from the textbook. Okay, once again, focusing on the textbook, because according to our point of view, the textbook never moves. But the coffee mug, it's sliding to the right. And this is really cool. Now, in actuality, in our frame of reference, what's happening, right? So here, it looks as if the coffee mug is sliding to the right. And that's because the frame of reference is the book itself. And so if we can say that the coffee mug is sliding to the right, and we know that friction opposes all motion, we can say that the force of friction is to the left. Okay? It's a really cool trick that you can do. But another way you can think about it is if you pull on the book, you're not exerting a force on the coffee mug, but the coffee mug also gets pulled. That must mean that the force of friction is pulling in the leftward direction. Okay? So you might be thinking to yourself, Mr. Lee, I thought we were doing centripetal motion here. This has nothing to do with circles. Well, let's do a practice problem. Now, I've seen this problem more and more in the AP exam, so I did want to focus on it. And so all that was just a big intro into this problem here. Let's say we have a Ferris wheel type of sorts, okay, a big circle. And this big circle, it mechanically rotates around, let's say counterclockwise. And this big circle has platforms. So we have a platform there, we have a platform here, we have a platform here, and we have a platform here. Okay, so as this Ferris wheel of some sort is spinning around, we can imagine that the entire Ferris wheel is also spinning around. And let's say that on top of it, we have, we used the coffee mug before. Let's use the coffee mug again. We have a coffee mug. Okay, we have a coffee mug right there. And I don't want to draw a coffee mug on each of the ones, but I'm going to draw a coffee mug on that scenario here, and I want to draw a coffee mug down here as well. Okay, all right. So if we have coffee mugs on all four platforms, and this object is rotating around, what is the centripetal net force equation for the coffee mug? Okay, now this is an important distinction because we know that the centripetal net force is used to describe a rotating object. Now, even though we know that the Ferris wheel, okay, the Ferris wheel, this is like a desktop Ferris wheel, so we could put a coffee mug on it, right? The Ferris wheel is actually rotating. But if we look at it, right, because the coffee mug is attached to the wheel, or it's not attached, but the mug is on top of the wheel, we can say that the coffee cup is also rotating in a circle. And so because it's rotating in a circle, we can apply the centripetal net force equation. All right. So let's do the bottom one first. I think this one's a little bit easier to conceptualize. So if I were to draw a free body diagram for the bottom one, okay, I would say that there is a force of gravity going down. And because the mug is traveling with the platform, we can say that there's a force of friction pushing the mug to the right. For all the same reasons as we discussed before with this idea back here, right? If we were to pull in the book. Now, so this should make sense, right? If the platform is moving in a counterclockwise circle, the platform is moving to the right, the coffee mug is also moving to the right, and we can say that the coffee mug is moving to the right because of the force of friction. So for this bottom one, if we were to come up with a net force formula, FSC is equal to MAC, if we were to identify the axis of rotation, so here's the mug, here's the middle of the circle, so any force along this dotted axis is the axis of rotation, we can say that the normal force, positive, not because it's pointing up, but because it's pointing to the middle circle, minus the force of gravity, is causing this object to rotate. All right, boom, equation. All right, so that's nothing new. But if we take a look at the 3 o'clock spot, all right, so if we were to come up with our net force formula, let's do this one in blue. I'll do blue for this one. We can say that the force of gravity is going down. Okay, we say that the normal force is pointing up. All right, so we have to use our imagination here. We know that this platform is going to be traveling along this rotating path, right? This circular path. And so as the path is moving up and to the left, the cup will also be moving up and to the left. Now, the tangential velocity of the cup is already vertical. And you're thinking, hold on, Mr. Lee, what do you mean? Well, if you remember, quick little detour, and I do want to pay attention to these small little details here because that really does add to this problem, right? If we have an object that's rotating around in a circle, I'll do this in red. If this is the center of the circle, right there, that is our tangential velocity, okay? So it's always going to be perpendicular to the edge of the circle. So here, this cup will be moving up and to the left, but currently it's just moving up, and that's because it is the tangential velocity. But now I want to focus the leftward portion. So it's going to spin up and to the left. It's already spinning upwards, but now it's going to be spinning to the left after, some time passes here. And so if it's going to be moving up and to the left, that must mean that there is a force that is causing it to move in that leftward direction. That's where this entire magical centripetal motion happens. And so the reason why that there's a force pointing the leftward direction is because there's a force of friction pointing to the left. Otherwise, when this platform is moving up and to the left, if there was no friction, this cup, it would just keep on moving up and up until it was at a point. So let's say, I just want to exaggerate this here. So this cup will be moving up, right? Because it's being raised up by the platform. But when let's say the platform is like right here, okay, if there was no friction to keep the cup in place, the cup will just keep on going up and it will slide off the platform. But thanks to the force of friction right there will keep it on the platform. So if I were to come up with a net force formula for this scenario right here, I would draw it like this. I would say that the net force formula is like this. We have to identify the axis of rotation. So that's the center of the circle. I'm going to make a dotted line to the object. And we can see that the force of friction is the only force that's causing this object to rotate. Okay, and we can, break this down even more by saying it's like mu times the normal force. Like, there's a lot of things that we can say here, but this is super cool. So this applies to when the object is at the 3 o'clock and the 9 o'clock spot, okay, as we saw in the previous video. But the force of friction is the only force that causes this object to spin in a circle, compared to when it's at the 12 o'clock and the 6 o'clock spot. And at those positions, the normal force and the force of gravity is what's causing this object to rotate. All right, so that was a long explanation into the mathematical side to it, but I need us to think about this conceptually. Okay, so I'm just going to take a couple more minutes to describe this conceptually. Let's look at the 12 o'clock and the 6 o'clock spot. Okay, the 12 and the 6. So we know that centripetal force causes an object to rotate in a circle. Okay, causes an object to rotate in a circle. So we have discovered, according to this equation, that the normal force and the force of gravity causes the object to rotate in a circle, compared to the 3 o'clock and the 9 o'clock locations. There, only the force of friction causes the object to rotate in a circle. Now, we have to understand this why conceptually for our course. At the top and at the bottom, so at position 12 and at position 6, the tangential velocity at the top, I'll do this in green, is to the left. Okay, the tangential velocity at the 6 is to the right. An object in motion will stay in motion unless there's an outside force. So what this means is that this object wants to keep on moving to the left, but it's not, because it's going to move in a circle. So what causes this leftward moving object to curve downwards? And that would be the force of gravity. And because it's on a platform, the normal force also helps here. So this is a huge leap. This is a huge conceptual leap that your brain has to make. So here at the bottom, right, this object, it wants to move to the right continuously. An object in motion wants to stay in motion. It wants to continuously move to the right. So what's preventing it from moving to the right? Well, as the object is moving to the right and the platform is swinging up and to the right, the object's going to be running into the platform. Okay, and because the object is like continuously running into the platform, that's where we get the normal force. So the normal force is causing this object to be lifted up. And because it's being lifted up, but it wants to move to the right, that's going to cause the rotating motion, the centripetal motion. All right, so if we take a look at the 3 and the 9, we sort of described it before, but here, let's do the 3 o'clock one because we did all our math for it. At the 3 o'clock motion, the tangential velocity is upwards. It wants to move upwards. It wants to continuously move upwards. So what force is going to cause it to move to the left? And we know it's going to move to the left because it's bound by this path, this rotating path. All right, so the question is what's causing it to accelerate to the left so that it's moving in a circle, and that is the force of friction. And the same applies over here, right? So if we have an object here, at this moment here, the tangential velocity is straight down. Okay, it wants to move straight down and wants to continuously move straight down. And so what's causing it to move not only down, but down and to the right, right? Because that's the path. And that would be the force of friction. The force of friction will drag it to the right. Okay, and that's what's going to cause the centripetal motion, the rotating motion. All right, so these are the more complicated versions of the centripetal motion problems. I just spent a lot more time on the Ferris wheel one because that really encompasses like a lot of the concepts of this unit and the previous unit. So make sure that you do take the time to absorb the lesson from the Ferris wheel problem. I've seen that problem popping up more and more over the years, and so I do think that it's worthwhile to spend a little bit more time on. All right. Other than that, this has been the Advanced Centripetal Motion Problems. I'll see you next time.